this really has two different ideas, tangent line and higher order derivatives. I'll explain. Let's first find the tangent line equation. Now we've been kind of touching on this. We have been finding the tangent slope at a point by using the derivative. Okay? Now we were just finding the slope of it. Now we're actually going to find the whole actual equation of the line, not just the slope. It's just, you're done your hard part. The derivative part's the hard part. Now it's just, using it plus a little more. So, goes a little something like this. If I wanted the tangent line to the square root graph at x equals 4, then I'm looking for this line that barely skims the curve at 4, 2. Changes just right with me. Now, the process goes a little like this. Point, slope, point, slope. The point is easy. The point, in this case, is given. A point on the line, which is actually also a point on the curve, they share that point. It's called the point of tangency. The point we know on our line is 4, 2. The y-intercept would be a guess, and anything else would be a guess. I know it goes through 4, 2. So far, so good? All right. Now, the slope, I'm going to communicate not just how, but the work I want to show. I want you to say, hey, I'm finding the slope. And I find the slope by taking the derivative at the point of tangency. So I want the derivative at 4. They, on the AP exam, grade for that. Did you communicate how you found the slope? All right, I found the slope by finding the derivative. Now, if f of x is the square root of x, then f of x is x to the half. What's the derivative of x to the half? By power rule, 1/2 x to the negative 1/2. Now, whether you know it or not right now what I have is a little bit of bad calculus. And this is something that we're going to gradually get to. I said here, I'm going to find the derivative at 4. But this is the derivative generally at any point. So in order for this to really be equal to this, you should say it's this at x equals 4. I would probably take some just that. But you should never show a mixture of general equals the specific. They take off of that kind of thing. It's derivative specifically at 4 equals that guy. Right? Now, if I go a little further, isn't this the same as 1 over 2 root x at x equals 4? X to the negative 1/2 is the same as square root of x in the denominator. So what do I get when I put in 4? 1, 4. Does that look about right? Positive slope, kind of flat on the picture? Yeah, seems good. All right. After you've got a point and a slope, we're going to write the equation of the line in point slope form. So in point slope form, using this point and this slope, my equation is y minus 2 equals 1/4 times the quantity x minus 4. Okay? I want you to just leave it like that. You're not going to impress me by putting it in slope-intercept form. You will possibly make a mistake and lose points. So leave it alone. All right? Point slope form is good. That's the idea of a tangent line. Now, would you try one on your own? Find the equation of the tangent line to the cosine curve at x equals pi over 6. If you want to draw a picture, fine, but you do not have to draw a picture. Point, slope, point, slope. Two-step process. Point, slope, point, slope. for x. How we doing? Looks like we're good. So the point, they give you the x, you need the y. Cosine of pi over 6 is? Come on, that's not hard, don't be afraid. Square root of 3 over 2. Okay, cool. F prime of pi over 6, that means we have to take the derivative. Yesterday we studied derivatives of trig. What's the derivative of cosine? You might not have it memorized, but hopefully you do. Negative x. Negative sine. Now, I first report the derivative generally, saying I'm about to put pi over 6 in, but I separate those steps. Right? I say the derivative is negative sine at pi over 6, that is negative 1/2. All right, I have a point, I have a slope. Now I throw it in point slope form. My equation is y minus pi over 6 or root 3 over 2? Root 3 over 2. The y value is the slope, negative 1/2 times parentheses x minus pi over 6. Okay, cool. All right, would you get out your calculator, please? Let's practice doing this in a calculator kind of deal. I need to open up my calculator. All right, would you put that function into F1? I'm going to use it in two levels. We're going to need the point and the slope. So we're going to need that in. So, all right. So what is it again? E to the side of x plus 3 tangent of 5x. I forgot, I scrapped this from my lesson yesterday, but your calculator must be in radians. All calculus is always done in radians, never done in degrees. If I ask you in radians, what's the derivative of sine, you would say cosine. But if I say in degrees, what's the derivative of sine, you would say not cosine. It's got to be in radians. So, if we have that in, do you have the function in? Does it look really pretty?
Yes.
All right, like wallpaper, cool. Let's go back to our home screen. We need a point and a slope. So to get the point, we're going to plug 2.75 into the straight up function. So call it the function f1. Evaluate it at 2.75 and give me 3 decimals. My point is 2.75, 8.822. Do you agree with my outcome there? All right, now we need the slope. How do I find the slope? The derivative. Okay, now, if you were in this Kansas class, you could probably take this derivative. It's chain rule, and so you know the chain rule. You're good. But us, we're going to use our calculator. How do you use your calculator? A calculator derivative? You go to menu, calculus, and the derivative is the first one. The variable is x in this problem. We often deal with t's, and no big deal. In this case, it's x. The value at which I want to calculate the derivative is 2.75. The first derivative, that'll make more sense in a second, but now leave it, hit OK. Now, it's saying, all right, great. What do you want me to take the derivative of? What do you want me to take the derivative of? The function f1. Okay, you need to tell, you could have 8 different functions. You have to tell it, hey, take the derivative of f1. So put in there f1 of x, take that derivative at 2.75, Well, and there's your slope. It's pretty steep, which makes sense with that graph. It was almost vertical everywhere. So the slope, now, here's the gotcha. It's tempting because you're using your calculator not to denote anything, just to write that down. You've got to communicate still that the derivative at 2.75 was used to get your slope. And that slope is 103.867 or 868. I don't care if you round or truncate. Is that clear? Question so far? What's step 3? Point slope. We got a point, we got a slope, point slope. Y minus 8.822 equals 103.867. X minus 2.75. Tangent line complete. Are you with me? Cool. All right, let's go on. Now, I mean, tangent lines are fun to find and all that stuff, but there's a purpose to it. Tangent lines are used to estimate things, big boy stuff, all right? Now, pre-algebra, if I said estimate square root of 5, then you would say, all right, I'll try 2.1 times itself, and now I'll try 2.2 times itself and see what gets close to 5. In calculus, you would actually use your tangent line to estimate the square root of 5. Now, here's how the thought process goes. I have this tangent line I found. It was the same as the first problem. It was y minus 2 equals 1/4 x minus 4. That was the first problem we did, right? That's our tangent line. Are we cool? Are you with me? Okay. Now, at 4 goes to our touching. We drew our tangent line at 4. So in terms of at 4, they are both exactly 2. You can see, though, that because the square root curves, the minute you go off a little bit, like to 5, there's a little bit of a difference there. It's hard to see, but there's a little difference between those two, right? But it's a very small difference. And so couldn't I just put 5 into my tangent line equation and say that's going to be doggone close to the square root equation at 5? And I would do that because square root of 5 is hard, but putting 5 into this is easy. It's linear. So we're going to put 5 into our tangent line equation, and we would get something like y equals 2. I'm going to move the 2 over there. Cool? 2 plus 1/4 of, and in place of x, I'm going to put a 5. I get an estimate then of 2 plus 1/4, 4, 2 1/4. That's a good tangent line estimation. Now, is our estimate, if you look at the graph here, is our estimate, we say it's 2.25. Do you think that's more or less than the true square root of 5? Use the graph as a guide. Is our estimate of 2.25 more or less than the true square root of 5? How many say more? Why do you say more? Yeah, look at the y value of the line versus the y value of the curve. The y value of the line is a little above the y value of the curve, and so our line y value is going to be a little more than it truly is on the curve. So it's going to be a little more because the line is above the square root curve. If the line was below the square root curve, then it would be underestimated. All right? What if we tried to estimate the square root of 6? Or the square root of 7? Here's the square root of 6. Here's the square root of 7. What happens as we get further and further away from 4 in terms of the quality of our estimate? The error, this difference between the two, this gap, is the error in the estimate. The difference between our line and the curve is error. And so the further we get away from 4, the more the error. As you get further from 4, more error. What if I wanted to estimate the square root of 8? I'd have a stinking lot of error, right? So what can I do to get a better estimate? If I wanted to estimate the square root of 8 accurately, then how can I change my tangent line? The point is, I'm trying to make is, you don't have to do it 4. You can have a choice. You could do the tangent line anyway. So where would be, if you wanted to estimate the square root of 8, where would be a better place to draw your tangent line? 8, now 8 would be great, but do you know the square root of 8? No, that's kind of the question. So when I say where else could you draw the tangent line, you want to choose one that square root's nice. So where's a good point that square root's nice, close to 8? So you draw a tangent line at 9. If you redid the problem at 9, then that tangent line would be very close to 8, and you get less error. So when you go to make your tangent line, you actually choose, what's the best place to draw my tangent line so that I'll get a small gap. You follow? Okay. Then you would make a tangent line at x equal 9 instead. That's it. Okay? All right. Now then, let's go through that whole process. Whether you know it or not, I kind of broke it into pieces for you. I said make the tangent line first, and then later on we did the estimate. Usually it's do all of that at once. So if I wanted to estimate the natural log of 2 using a tangent line approximation at x equal 1, then you first need to make the tangent line. Actually, that's what this step's over here, darn it. Make the tangent line, f of x is natural log of x. I'm trying to estimate the natural log of 2. The point at which you draw the tangent line, they tell you using a tangent line approximation at x equal 1. So the point is 1 and natural log of 1, which is what? Natural log of 1 is 0. Okay. All right. Would a picture help? Does a picture help you a little bit? No. Okay. All right. Now let's do a slope. How do I find the slope of the tangent? The derivative at the good point. All right. So the derivative, if f of x is natural log of x, then I want the derivative at the good point. The good point is 1. All right. This is my quote unquote good point because I know natural log of 1. I don't know natural log of 2. So I'm going to go at 1. F prime at 1. Let's start with the derivative of natural log. 1 over x. And we want to evaluate that at 1, which is 1, obviously. So what is the equation of my tangent line? Y minus 0, if you like, or just y equals 1 times x minus 1. I guess you could just say y equals x minus 1. Cool? After you have the tangent line, then you use your tangent line to estimate log of 2. Okay, what does that mean? What do I do? Rather than put 2 into the natural log function, which I don't know, that's the whole problem, I put 2 into the linear equation. Put 2 into the tangent. Y equals 2 minus 1 or 1. So we're claiming that the natural log of 2 is about 1. Despite the fact Rainey said no picture, I'm doing it anyway, doggone it. Here's the idea. This is the natural log curve. I did a tangent line at this point. I then put 2 into my tangent line and said that's a pretty good idea of what the log of 2 would be. There's a little error there. Okay, so our estimate is 1. Cool? Is there not a U try there? Okay, you try. I do not have that here. First thing you're going to want to do is say what's the function. In this case, the function is the cube root of stuff. Okay? And we're trying to say what is the cube root function when you put a 7 into it. You don't want to use a tangent line at 7 because 7's not clean. So you want to find a good point that cube roots nicely near 7. So you use 8. Oh, I usually use this one. Some solid algebra skills. Exponent of negative 2/3 in your derivative is kind of gross, right? So take it piece by piece. The negative means denominator, the third means cube root, and the 2 means a square. So what's your slope? 1/12, exactly. 1/12. So I hope you got a tangent line of y minus 2 equals 1/12 times x minus 1. Yeah? All right, am I done? No, now we use it to estimate. What do we plug into what? We're trying to estimate the cube root of 7, so we plug 7 into our tangent. Y is, I'm going to move that 2 over so I know what y is by itself. Y is 2 plus 12 of 7 minus 8. That's 2 minus 1/12, which is 1n. 11/12, yeah? Why would the cube root of 7 be a little less than 2? Cube root of 8 is 2, so cube root of 7 should be a little less than 2, right? So that makes sense. All right. Run out of time. Sorry. Move on to higher order derivatives. Higher order derivatives is to say taking derivatives of derivatives. Not just because it's fun to take derivatives and you're trying to maximize fun, but because it has a lot of applications. You could talk about how a curve shapes by looking at the second derivative, looking at concavity. You could talk in physics about acceleration. Acceleration is the second derivative. So the second derivative is needed. So First of all, notation. If the original equation is y, then the first derivative, or the first derivative, could be either y prime or dy dx. Those are both pretty common notations you'd see for a derivative with y in it. The second derivative would either be y double, this is an or, not both of those, or, and this is the one that scares students because they get the 2's in the wrong place. The second derivative, Leibniz style, looks like that. Now, why that is, I'm not going to go there for a while, but it is the second derivative twice over, or the derivative twice over of y with respect to x. Either way, most students don't feel comfortable that way. If you have function notation or Newton's notation, it's f prime, obviously, for the first derivative, and f double there. That's what I just said is pretty much how a calculus person in the know would say it. F double. It means the second derivative. Actually, get that in your notes. This is read as f double. I guess you could call it f double prime, but most people just say f double. Okay. Now, if then, in this example, they ask you to find y double at 1, then you're going to have to take the derivative twice. First, find y prime. What is y prime? What's the derivative of 2x squared? 4x. What's the derivative of 3? 0. Leave it out. What's the derivative of e to the x? E to the x. And what's the derivative of natural log? 1 over x. Now that's y prime. Notice I say that's y prime at all x's. I'm not going to put 1 in until I get to the second derivative. So don't sweat the 1 right now. What's y double at x? Or y double, generally speaking. What's the derivative of 4x? 4, right? That's x to the first. The derivative would be 1x to the 0, which is just 1. And so the derivative of 4x is 4. Cool? Derivative of e to the x is e to the x. This one, I might mentally rewrite this. 1 over x is the same as x to the negative first. What's the derivative of x to the negative first? Bring the power down. Negative 1, x to the negative 2. All right? That's y double at x. Now I can say y double at 1 by plugging 1 in. Y double at 1 is 4 plus e to the first, or just e, minus 1. Or I guess you could say 3 plus e. Cool? All right. I think that's good. I'll leave the other one. All right. Questions on, I would normally do a wrap up, but let's go here. Do we have, you stop 25 questions. I want 25 today, at the very least. 25. Make sure I get 25 today. What do you got, if anything? I do have some stuff online. Start 6 on hard copy. 22.
Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
I don't know if it's 26.
The first girl lettering meeting will be tomorrow in class. We will post your assignments and mention your mentor pairs on the bulletin outside the cafeteria today.
Is this changed in any way?
Hey Dad, come and pick up your Dublin Jaguar stickers from the cheer team at both lunches. They are only $1, so do not miss out. There will be a robotics club meeting tomorrow during 7th hour in the computer lab at E202.
Okay, So the first thing you want to do is you need to get some H action. You need to know, well, what is H around here? This table is all about F and G. So the first thing you want to do is, what is H at each end? So if I want H at 0, then that would mean H at 0 is F of G of 0. G of 0 according to the table is 2. So I plug that into F. F of 2 is -1. So H is at -1. Then do the same at 5. F of G of 5. G of 5 is 0. F at 0 is 3. So it looks like H went from -1 to 3. Must have been 2. Or yeah, if it went from -1 to 3, it has to pass through 2 on the way. So that's when you say our IDT. H is continuous. Actually, I don't even know if I told you it's continuous, but let's assume H is continuous. And that H equals 2 is between -1 and 3. That point they asked about too, it's between the two endpoints. So by IDT there must be a point where H equals 2. Does that make sense? Okay. One still question. Okay. So number 1. Yes. In fact, I can also put these on my website if you like. So you have. What else? Do you know what? Is anybody, if I run out of time, is there any other question you want?
17 and 19.
17 and 19 on my website. I'll do those at lunch. Okay. So this won't take long. Let's answer this. 24. Did you say? Okay. They want the distance between those two. Now, the first start is distance coordinate. This is the distance coordinate. Which in this case then would mean x minus 3 squared plus y minus 4 squared. Okay? Now that's a start. Then it says, they say in terms of x only. So now the next goal is, what can I put in y's place so that this is in terms of x only? Well, that's where this equation comes in. If y equals x squared, then I can put x squared in y's place, so it's Did I get you started? Okay.
So it's 25 due today.
25 due today. Let's see your questions online. I don't try to get 25 today.
And you left your height.